I'm going to provide you an interesting lecture now, one on unconventional gas fracking and groundwater. There's been a lot of information in the media, some of which is confusing, and so I thought I'd provide you a background bit of information on how to potentially manage risk associated with fracking. The important thing here is not to talk about opinions or to infer anything from what I'm saying, but I'm just going to present you with some useful information that perhaps you can actually use to come up with your own views on fracking and its risks to groundwater. First of all, it's important to try to understand really how far under the ground are people talking about when we're talking about fracking for shale gas. Oftentimes, when you're drilling for oil, you'll drill many kilometers into the Earth's surface to find oil. And the same thing happens for these deep confined geological units that contain shale gas. So when we're talking about groundwater, usually you might find the deepest wells are going down to a kilometer or so. Oftentimes, most wells, groundwater wells, are in the 75 meter to 300 meter depth range. And so when you're talking about 2.5, 3 kilometers down, you're talking about substantial distances into the ground. So to give you an idea of the differences, if you were to hold your arm up and look at your middle fingernail, that's about the depth that you'd find an awful lot of shallow groundwater at. And the shoulder is about where you'd actually be looking for shale gas or other unconventional gases in the subsurface. As we've been talking about, hydrogeology is that interface between earth sciences, earth materials, the rock, any sediments near the surface, and the fluids that are flowing underneath the ground. And those fluids might include gases like shale gas. And of course, as we talked about before, the geological processes of the subsurface are oftentimes managed and enhanced through water movement in them. So therefore, water is a primary agent of many geological processes, and in fact, in these shale gas type deposits, they'll be fully saturated with water as well. When we talk about the aquifer is that geological formation that is transmitting economically potentially important quantities of water, and usually we're talking about unconfined or near surface aquifers that we're using for getting a water supply from. Of course, there's deeper aquifers, those confined aquifers, in which waters can be many centuries to millennium old, and therefore, when people start thinking about deeper groundwater or groundwater being impacted by even deeper activities such as oil and gas exploration, this is why people tend to worry about contamination issues, because the water in these deeper units are quite old to begin with. So, Derek Ball has given you some lectures on the Aviemore Valley Aquifer, and this aquifer system is a shallow aquifer system. It's in a deep glacial valley, and this deep glacial valley actually has sediments ranging up to 80 meters in depth. And those deep sediments are actually turns out to be a gravel layer that is providing a huge natural resource for water. So when you look at the aerial extent of the number of boreholes that were put in both for trial and for development of the groundwater resource there, you could see how much and how wide of a land area was actually impacted during the development of that water supply. And in fact, when you start looking at both the testing and the development program, it's not dissimilar to what you'd find in other drilling for oil and gas. The drilling rigs are not dissimilar in shape and size. In drilling for shallow sediments, we'll be using drill bits that are not unlike some of the drill bits that you would be using when you're drilling for shale gas and others. And important when you get to the construction of the entire borehole supply, the size of the impact or the amount of activity that you'd be looking at for developing a commercial or a public supply water supply is not dissimilar to the footprint that you'd have for developing of a shale gas. And in fact, when you're looking at the production of borehole drilling and testing, you'll be looking at managing water and wastewater issues. You'll be looking at abunding the areas to make sure that any of the drilling fluids are not going to be contaminating the shallow areas or the ground nearby. And so many of the health and safety and risk assessments associated with drilling activity for drinking water supplies apply to the same health and safety risk assessments that you'd have during a fracking or other unconventional gas drilling exploration. And in fact, when you're looking at pumping tests and managing water, you're oftentimes managing huge volumes of water during pumping tests or during drilling of public water supplies, which is not dissimilar to the drilling that you're to be taking place in fracking. So in fracking, people are worried about dealing with wastewater or water that's coming up from these deep boreholes. But in fact, when we look at what we have to do for testing of aquifer materials and aquifer properties for a public supply borehole, it's the same order of magnitude of preparation, planning, and implementation that you have for testing of these resources. Of course, people say, there's this big public concern about contamination of groundwater associated with shale gas or deep fracking or other activities associated with energy generation. And so one thing I think we should go back and look at is where might these actually be, and what are the existing risk-based approaches that allow us to manage the potential groundwater pollution. For instance, there's risk assessment per the contaminated land regime, and there's also risk assessment associated with the groundwater directive of the European Union. So when we look at the potential impacts that are happening right now, we should realize that there is existing legislation and existing ways of managing these risks. So when we think of groundwater as a receptor or groundwater being at risk of contamination from something like fracking, we should realize that there's already legislation and policy in place that requires that if there's surface or subsurface potentials of contamination, that the risk to the groundwater body is evaluated, the pathways of that contamination from where it is to whatever receptor it might be, whether it's a community user, an aquatic ecosystem, or the environment in some ways, is managed. And so the reality is, right now we have in place legislation to help us to manage the risks associated with fracking activities. And in fact, if you start looking at the existing knowledge base that we have, there's an awful lot of work that's been done already on the risks of things like contamination of chromium in soils, or contamination of oil spills, or site-specific contamination maybe from petrol stations or other industrial activities. Therefore, we already know ways and have significant experience in how you take data like this, which shows a risk of certain locations of contamination, and make sure that the people living in and around there or passing through, or the natural resources, the groundwater and other things, are well protected from potential sources of risk. For instance, there's oftentimes leaks which come from simple things like accidentally breaking a pipe for home heating fuel. And so there's in place a whole both consulting and contracting series of solutions to problems that specific homeowners might actually come against, like home heating fuels. In addition, we can look at septic tanks. There's loads and loads of private water supplies, and importantly, people who are still not on mains wastewater treatment. And so there are regulations in place and permits and other things that are in place that provide for the safe and appropriate use of things like septic tanks in individual houses in rural communities to reduce the possibility of contamination of public and private water supplies. And of course, every time you go to put in petrol stations, or every time you go to put in an industrial activity, there is IPPC licensing, there is risk assessments, there's management, and importantly, ways that people have to actually evaluate and monitor these activities to make sure that the risk to contamination of both the soil, people's homes, and of course groundwater as a receptor is in place. When contamination does take place, there is also a plethora of remediation strategies, risk assessment strategies, and cleanup strategies that are in place already to manage the cleanup of groundwater. And of course, when we're talking about large industrial sites, there's been an ongoing program for decades now where industry goes about due diligence and evaluates whether or not there was or is an potential impact on the environment. And under licensing, they have to actually manage the risks to those environments. And where contamination may have actually spilled into the environment, they have a duty and a responsibility to clean that up. So many companies and industrial partners currently undertake significant amount of work and understanding, both in research and in application, for managing source pathway receptor linkages to reduce risks within the environment. And of course, there's risks from things like the agricultural environment, use of pesticides, fertilizers, nitrates, slurries. These all activities are also managed. The nitrates directive, certain farming practices, the utilization of different pesticides and herbicides on the land, and the spreading of sewage sludge is an important aspect that's all currently managed, and it's managed within a risk-based strategy. So there's been plenty of research, plenty of development of technology around how do we actually manage risk within the environment of specific activities. So when we start talking about gases in the subsurface, in particular the types of gases you'll get from fracking and such, these similar types of gases actually have the potential to impact groundwater from landfill sites. So there's already been studies on what happens to the natural microorganisms, what happens to the aquifer systems, and importantly, how these aquifer systems can be protected from those types of gases where they might actually enter into the groundwater system. So let's go back and look at that difference. So in groundwater, there's impact during the development of public water supplies. There's impacts potentially from rural and diffuse sources of pollution, and there's potential impacts from point sources of pollution as well, either from industry, from local activities like petrol stations, or from landfill sites. And that risk management of contamination of those groundwater systems is a well-established both consulting and contracting series of solutions that exist throughout the world. So when we look at the impact on the lower right there from unconventional gas fracking, we have to ask ourselves, well, how much different is natural, or the way we go about collecting groundwater from the natural environment to the way that we're actually collecting gases from the deeper natural environment? Well, first of all, there's a huge amount of experience within oil well drilling. It's been ongoing for well over a century now. And the techniques for drilling, both vertically and horizontally, are significant. This is probably where you deviate from water well drilling. It's because water well drilling is designed to capture as much water in a more confined and focused area than you would for oil. Oftentimes you have to drill for oil where it's easy to drill or get the oil to the surface, but the actual oil beds or the geological formations that contain the oil can be in much less accessible areas, and therefore you may have to drill a long distance away to reach those oil fields. So let's ask, what is the experience that we currently have on fracking in the UK? And on top of that, how we might then be looking at the differences of fracking versus getting groundwater as a resource, and then how we might actually use existing remediation technologies or risk-based technologies to minimize the impact of fracking. Well, first of all, there's a review that was carried out in 2012 that I think it would all be worthwhile for you to go and find. looking at what hydraulic frac has happened in the past and where it's going into the future. The points that you see on the right there, the dots, are places where fracking has actually taken place in the past. And there is actually considerable experience on fracking already within the UK and other places overseas. And in fact, the first shale gas exploitation well that was drilled in 1902 at Heathfield Station in Sussex. This was a 377-foot deep shale gas well that was used for lighting. Gas was also produced from oil shale at Broxburn in Scotland 160 years ago. And there were up to 200 oil and gas wells that have been hydraulically fractured at Winch, for example, at Winch Farm and other places across the UK. There's been underground coal gasification trials carried out in the 1940s and 50s, and the Lurgy high-pressure gasifiers that were used in the generation and use of these types of materials were developed here in the UK. So from a technological point of view, and from an engineering point of view, the exploitation of shale gas has been around over 100 years already here in the UK. So we should probably separate this discussion into a couple of different things. First of all is the difference between unconventional gas and underground coal gasification. The latter, underground coal gasification, is produced through controlled subsurface carbonization and combustion of the coal. So in this case, it's actually ignited or heated up to actually get combustion happening and release of the gas. So there is a step here where you're adding significant amount of risk associated with trying to control a combustion in the subsurface. Whereas if we look at unconventional gases are trapped in impermeable or slightly permeable geological formations. So tight gas would be in these impermeable geological formations, so you'd have to actually break them up to get the gas back out again. Shale tends to be have bedding planes that are easily fractured. And within the porosity, the fractures of these bedding planes, you can actually get significant quantities of gas that's actually stored. If you could break apart these fractures and break apart some of the space between the sand grains or the silt grains, you can get economically viable quantities of gas out. And of course, in coal beds, oftentimes you get microbial activity in coal beds that actually produce gases in these coal beds on a natural basis. And so drilling into those, oftentimes you find gas available in coal beds. So when we start looking at natural gas resources would have been within some kind of sealed geological formation, and the gases would have been trapped within pockets within these conventional geological formations, oftentimes very deep and associated with either oil, gas, or shale gas. So when we're starting to talk about conventional gas, you would hit through one of these sealing geological formations and come up with the gases under high pressure, which then would be released to the surface. Shale gas is caught up in these geological units here that doesn't naturally migrate out of the higher porosity units, and therefore what you have to do is you have to actually go in, break open, and produce more porosity for those gases to actually come and be utilized at the surface. So the public concerns over unconventional gas have been listed to the lower left here. Of course, seismicity and fracture propagation is an area around the enhancement of seismic activity and earthquakes. Of course, the water that's being abstracted and used within shale gas, and the contamination of groundwater, those two things are where I'm focusing here. Of course, there's emissions, including greenhouse gas emissions, and land values and public health potential issues. In this talk, I'm only talking about the second 2 points, water abstraction and use and groundwater contamination. And you'd have to look further afield for the impacts on seismicity, emissions like greenhouse gas emissions, and social impacts and land values. So what happens within fracking? Well, first of all, you have to actually drill a borehole down to the zone that actually contains the shale gas or the unconventional gas. And in the upper reaches where there's potential sources of groundwater that's can be utilized, you would actually undertake to make sure that you had a series of grouting and different mechanisms to keep the geological formations here from the activities that would be happening at depth. And oftentimes you'll find that you have three or more possible casings that are putting in here to seal this off, which have cement and other things. Because not only do we want to protect the groundwater from the activities down here, but the people who are actually getting the gases back out don't want to lose good quality product to shallow deposits. For them to have an efficient and economically viable abstraction of these gases, you have to make sure that these gases aren't being lost on their travel back up to the surface. Once you're down and you've turned the corner and you're down into these geological units, you'll then use a perforation gun, and that perforation gun produces slight explosions that will then slightly fracture the geological formation. And once you've fractured that geological formation, you force in water and others substrates to try to keep those fractures open so that the gases can move through the fractures once you've removed the water and move into the well, and they then back up the well and being collected at the surface for utilization. So a lot of people worry about the amount of water that's being utilized and potentially contaminated here. And the average well will use up about 20,000 cubic meters of water, or about 500 tankers worth of water. Now, to put that into context, let's look at a local wastewater treatment plant here in Glasgow. The Dalmuir plant serves over 650,000 people in the surrounding areas of Glasgow and treats on average per day 378,000 cubic meters of water. So the 20,000 cubic meters of wastewater from a fracked well is equal to about 90 minutes of the treatment of water that would take place at this wastewater treatment plant. So that sort of puts some idea into perspective of the volumes we're talking about compared to what we're flushing down the toilet on a daily basis. So one of the other things to look at is what is currently published on the impact of deep unconventional gas exploration on groundwater. And again, this is not about seismic activity. This is not about greenhouse gases. This is only about the direct impact on groundwater itself. So there was a study in 2014 done in the United States, which looked at the impact in Pennsylvania on the Marcellus shale gas and the shallow groundwaters that were in that area. And I'd advise you to go and have a read of that report. So essentially what they were looking at is they're looking at the potential for the activities and the fracking activities that were happening. And these are the fractured depths in feet. Of course, this isn't feet because it's the United States. The fractured depths in feet and their interaction with the fractures and the wells that were actually drilled in the overlying hydrogeological units. So you can see some of these wells that were drilled in the overlying geological units are quite deep, maybe up to 2,000 feet. But there's still a significant difference or distance between the wells and the fractures that were produced for shale gas and the depths of the boreholes. So there is a space in the subsurface here that separates the fracking activities from the water supplies above them. And so one of the things we should probably start thinking of is how can we, in looking at these aquifer systems near the surface and these activities in the deep surface, how can we make sure we start using the normal source pathway receptor risk management strategies that are there for groundwater already? And how can we use the existing legislation to manage and, more importantly, control the potential environmental impact of these unconventional gas investigations and utilization? Well, of course, we already know that there's quite a bit of potential of methane getting out of these systems or other gases getting out of these systems, causing contaminations in the near surface groundwater. But there's already significant bodies of literature on these gases from landfill sites impacting groundwater as well. Not only that, we also understand the natural attenuation of these contaminants and what it does to the water chemistry as that's going along. And you should learn more of this in your contaminated land courses. But this natural attenuation does occur, and there are natural microorganisms that are capable of breaking down these gases in the subsurface, and it really requires an understanding of the amount of oxygen, the amount of gases, and therefore the stoichiometric balance of that to make sure if anything does get released that it can be cleaned up. And of course, there's lots of engineering already in place on how to actually separate and protect geological and hydrogeological units from production zones. There's already, across the UK and of course here in Scotland, aquifer vulnerability maps that are available. And these vulnerability maps can be lain over and evaluated with respect to the coal deposits, coal gas deposits, or fracking that might be there. And with these vulnerability maps were developed to manage the risks from other activities like industrial activities, small-scale industry like petrol stations, or from farming and agricultural diffuse pollution. So because we already have this mapping of risk, we could potentially work on a bottom-up in the sense of deep geology to the surface risk, and take these groundwater risk vulnerability maps and actually develop deep vulnerability maps and look at what is potential vulnerability from these deeper geological units. We already have environmental forensics techniques, some of which are pioneered here at the University of Strathclyde in our hydrogeology research group. And in this hydrogeology research group, we already are looking at contamination from the gas industry by looking at coal tar that came from coal gasification 100 to 150 years ago. And we can look at the specific contaminants that are coming up and fingerprint where they came from and what the original process was. So when we're looking at new processes like deep shale gas or looking at coal gas, it would be possible for us to actually fingerprint these different sources, and therefore, should any contamination happen, identify which target industry or which company actually was responsible for the release of that into the shallow groundwater systems. And there's a plethora of remediation technologies that are already out there. So should some kind of contamination occur, there's already a huge toolbox available for cleaning up groundwater and managing the risk from contaminated groundwater. So one on the left here, the Cerebar Permeable Reactive Barrier, is a project that was led by myself, funded through the UK and one of the gas industries, National Grid. And this project here is still operating and making sure that the risks of some contamination, which happened over 100 years ago, is still being managed and that the groundwater is protected for the people living nearby. So these types of technologies do exist, and the infrastructure on risk assessment, legislation, and policy all currently exist for protecting groundwater supplies. So in summary, when we start looking at the risks from unconventional gases, the risk management strategies currently exist for groundwater as a receptor and as a pathway of contaminants. This risk-based technology exists as well for groundwater, both as a receptor and as a source of contamination. There's already significant engineering knowledge for hundreds of years on well integrity to manage the risks to groundwater. And there's already currently high standards of these implementations. There's some excellent global drillers that are based here in the UK. Public concerns over contaminated land and underground contaminations are similar. But it's quite interesting that we find that these unconventional gas types of concerns that we see in the newspapers and such are much more prevalent than we hear about contaminated land. And so therefore, encouraging science and technology sharing between the 40-year history or more of contaminated land remediation and groundwater remediation technology development unconventional gas exploration and exploitation is a fruitful way, basically, to look at the risk-based management to groundwater from unconventional gas sources and manage them in a way that the public already accepts that we're managing contaminated land. And of course, as I said, environmental forensics techniques do exist to uniquely identify sources of contamination, should they actually exist. So this is one of the reasons why I wanted to introduce this to you with the MSc here in hydrogeology at Strathclyde. Because we're already teaching students about these risk assessment methods. We're already teaching them about source pathway receptors. We're already teaching them on how to utilize and manage groundwater resources most effectively. And importantly from that, they would then be the next generation to make sure that any unconventional gas exploitation is actually managed appropriately.